So this is the lectures for my section of the Chemistry of Everyday Things unit. So my section's all about light. Now I'm just going to quickly explain a little bit about the format of these lectures, because obviously this isn't normal. So what I'm doing is I'm going to record all of your lectures, so everything that you get in your handouts is going to be recorded and shared online. And what I'm going to do in the lecture slots is I'm going to do a few activities and get you to do a few things as well. So what will you learn in my section? Well, I've had 3 lectures and I have 3 slots, and I'm going to break that down into 4 recorded lectures. And essentially, I'm going to do a little bit about what light is, how our understanding of what light is has changed. Then I'm going to do a small amount on the sources of light. So, the differences between different types of light bulbs or LEDs or things like that. Then we're going to look a little bit about the absorption and the emission of light, what gives colours to everything around us, essentially. And then I'm finally going to finish with some of the chemistry that we can do with light. So, hopefully you've all seen something like this before. This is the electromagnetic spectrum. We have it going from high energy to low energy, and the bit that we think about usually as light is just the bit that we can see. So at the high energy end, I have X-rays and gamma rays. Now, there is no difference in the wavelength of X-rays and gamma rays. Lower in energy, longer in wavelength, we have UV light, and then we have the portion of the spectrum we can see. Highest in wavelength is red, but that's lowest in energy. Highest in energy, lowest in wavelength is our violet. We move further down into the infrared. Initially we have the near infrared, which is a bit like the light that we see. It's just a little bit outside of our range. Then we have the longer wavelengths of infrared light, the lower energies, which are more what we think of as thermal kind of sources. Below that we have microwaves, and then below that in energy, longest wavelengths of all, we have radio waves. So I'll refer to this spectrum a lot, and it's kind of useful to kind of have an idea about these energies and things. So the story of light begins about 300 years BC, when Euclid worked out that light travels in straight lines. Light couldn't come around a hill, it couldn't come around a corner. You could only see light that was passing in straight lines straight towards your eye. He also put some mathematical laws on the processes of reflection, so how mirrors work and how light is reflected off the surface of lakes and things like this. So that's our first understanding, very, very important. Light always travels in straight lines. Largely our understanding of light didn't change a lot in the next 1900 years. And the next person to come along was Isaac Newton, and he was the next person that had a really big effect on our understanding of light. And that's because Newton worked out that we could take sunlight, white light, and we could split it into its constituent colours, our visible spectrum. But then, what the new thing about this was that you could then take that visible spectrum and recombine it and get white light back. Now, there were all sorts of kind of religious superstitions at the time which basically said white light was pure and you couldn't make white light. And this was quite a big change in our understanding when Newton had worked out with a prism that you could recombine the spectra. Newton also said that light was intrinsic to light itself, not the colour it hits. He worked out that you could kind of make something look a different colour depending on what colour of light, what wavelength of light you would shine on it. So he worked out that if you kind of take, creamy yellow parchment in white light and you shine red light on it, it looks a different colour. Again, this was a change in our understanding. It used to be that we thought that light radiated from all objects. And so this is us heading slightly more towards the fact that light is around us and it bounces off objects, and we see colour based on what that bounced back light is. In other kind of big changes, Newton also built the first reflecting telescope. So this was using mirrors, not just kind of traditional optical lenses. And the benefit of having a reflecting telescope is that there's no chromic aberration or change in colour. So we hadn't quite got glasses perfect in the kind of 17th century. And therefore any glass lens was absorbing certain colours of light, which meant that when we were looking through at things, we weren't seeing what we thought we should be. So Newton had this idea that light was made of particles that he called corpuscules. He thought that when things refracted, so we hopefully you should know a little bit about things like real and apparent depth. And he thought that this refraction was caused by a slowing down of these particles in the different medium. And finally, he thought that you could convert between light and matter. That's how a candle worked. It took matter and it turned it into light. So Newton was really interested in light and colour and did a huge amount of work on all sorts of aspects of light. But one of his most famous papers, which is the one where he describes the recombination of the spectrum into white light, is actually available for you guys to look at. It's in a journal called Philosophical Transactions, and it's really rather sweet to look at. It's not at all how we write scientific journals, but it's available if you want to have a look at it. So a contemporary of Newton was Hooke. Hooke was equally as good as Newton, but got something of a bad press by Newton. You've probably all heard of Hooke because of Hooke's law, which I think you still do at GCSE with a spring. But Hooke was convinced that light was a wave, and the oscillations of this wave, he says, were perpendicular to the direction of propagation, which is remarkable when you consider the age. Hooke was very interested in kind of polarizers and things like this, and he built the first microscope and was actually using the optics of microscopes to draw the most amazing pictures of tiny little insects and things like this. And the polarizers were vital into looking at those insects. And he also managed to elucidate some things about colour as well, using these polarizers. Again, another contemporary was Christian Huygens, and Huygens was the guy who kind of came up with the biggest scientific mistake, probably of multiple centuries. It was something that put back our understanding of light for decades, if not centuries. And he said that light is emitted in a series of waves, much like Robert Hooke, but he said that those waves travelled in something that he called a luminiferous ether. The idea was that if waves travel through water, there has to be a medium for light to travel through as well. And they hadn't really kind of come up with this idea of air around us or things like this in quite such a solid manner. You know, if it wasn't something material, you couldn't hold on to it. And so he said that there was this, he basically equated the air as a luminiferous ether, but then the luminiferous ether was not just the air around us, but it was the contents of space, and it was the contents of everything that light could travel through. So again, we get a bit of a pause. We had kind of two great thinkers and Huygens, and we get a bit of a pause until Thomas Young comes along. And Young was absolutely fascinated with what happened when you put light through narrow slits. And he basically was the first person to kind of really study what we now call it as diffraction, and more particularly the interference pattern, which is caused when we have two narrow slits and the diffraction pattern coming from them. This was now incontrovertible proof that light must be a wave. And on this next slide, I kind of show you how that came about, in that we have these, this top basically shows the pattern that you see as you pass light through two slits. And we have very bright regions, and then we have completely dark regions. And that comes about from having either constructive interference where the two waves meet and they're perfectly in phase. If they travel slightly different distances, they'll be out of phase a little bit until we end up with them being completely out of phase, and we end up with these regions of dark patches. This is all based on the fact that these waves of light have travelled very, very slightly differences from these two slits. So, wave theory of light was now pretty well established. Newton was wrong, Hooke was right, Thomas Young had proved it. Now, probably the greatest scientist of the 19th century, certainly a scientist that Einstein looked up to as, the absolute great that had preceded him, was James Clerk Maxwell. So Maxwell came up with 4 incredibly important equations. I do not expect you to know them. I do not expect you to understand them. But these equations link an electric field, which is here represented by an E, and a magnetic field, which is represented by a B. And we can see in 2 of these equations, we have interrelationships between E and B. The electric and the magnetic fields are related to one another. And so Maxwell had concluded that light must be an electromagnetic wave. He also managed to work out that light travelled with constant velocity in a vacuum, and he managed to put an incredibly accurate figure on that for the time. Again, Maxwell is one of those figures that is perhaps a little bit forgotten, but our modern world would not be the same without him. His paper here, which is far more like our modern papers than the paper from Newton, is again available for you to look at. This paper is perhaps less understandable for you in terms of it's quite physicsy, but again it's a really interesting read. So by the time we had Maxwell and Young, light was very much established as a wave. And so Michelson and Morley came along, and they basically decided to look at the speed of the Earth. That's what they were trying to measure. And they were trying to measure it by having the light travel 2 different distances. And what the theory was light should travel the 2 different distances. As the Earth moved, one of the paths would be shorter, and so they would be able to work out how far the Earth had moved, and therefore its speed. There was a problem to this, though. It didn't work. No matter what they did, it didn't work. They always ended up with the same results. And ultimately, this experiment ended up with the conclusion that this luminiferous ether that had been proposed by Huygens and had been around for hundreds of years by this point was untrue. For huge amounts of time they'd been trying to find this thing, they'd been trying to explain it. And actually, as a side effect of this experiment, there was no luminiferous ether. And so this ended up with Michelson particularly ending up with egg on his face, because he had rather unfortunately said not long before that we know everything there is to know about physics. Not quite those words, but essentially we now know everything there is to know about physics. Move on, do chemistry, do biology, physics is done, we're sorted. You'll notice that there's a few very famous scientists I haven't yet mentioned. And this is where our understanding kind of changed. There had always been kind of anomalies, strange things with our understanding of light. So one of them is what we call black body radiation. So here I have basically the emission spectrum, so how much light of different wavelengths is emitted by bodies of different temperatures. This was well understood. It was so well understood that a potter, Josiah Wedgwood, had managed to work out what temperatures all of these things were. So, regardless of temperature, light will always, or bodies will always emit light. And if two things are at the same temperature, they will always emit the same colour of light, or the same spectrum of light. If I go back before, anything at 5,000 K will emit this spectrum. It will be largely focused around 800 nanometers, but it will be very broad around either side of that. But this shape, this kind of strange shape to this distribution, wasn't what was expected. The shape that was expected is shown here in this dashed line. We can see that it increases and continues to increase as I move to shorter wavelengths. Now, if you remember what I said kind of on my very first slide, wavelength and energy, they're opposites. Shorter wavelength is higher energy. This was called the ultraviolet catastrophe because basically it said that things should start to emit with higher and higher and higher and higher and higher amounts of energy coming out of it. And that was unsustainable. Essentially, the consequence of that is if I stand in front of a fire, I will melt. I will just be kind of exposed to all of this gamma radiation and I will just fry. And that's not what happens. I stand in front of my fire, I get a warm bum. So what happened was Max Planck managed to come up with an empirical observation, an empirical equation that fitted this result. But the only way to do that was to say that energy is quantized. That you can't just keep on giving out more and more and more and more energy. Energy has to come in packets of certain sizes. In this equation, I, on my left-hand side, my intensity of my light at any given wavelength, is proportional to a combination of factors. One is the wavelength of light, this lambda. Another is the speed of light, worked out by James Clerk Maxwell. It also depends on this constant Kb, the Boltzmann constant, which had been worked out about 20 years before. It depends upon the temperature, but it also has this constant h in it. H is now known as Planck's constant, but this was the constant that Max Planck realised he needed in order to make light fit into quantized units. This constant is the only way that he could make these kind of patterns, these spectra of light from different bodies match everything else he knew about it. So Planck completely blew away our understanding of light. All of a sudden, we couldn't have a completely linearized situation. We had to have quantized energy levels. And this fitted an experiment that was done just a few years later by Albert Einstein. The photoelectric effect was really well known. Everybody knew about it, but nobody had managed to explain it to how it works. Classically, the more intense the light, no matter the wavelength, the more electrons are emitted. So red light, bright red light, should emit more electrons than low intensity, weak blue light. This wasn't true. The intensity of the light would kick out more electrons the more intense it was, but some wavelengths of light, no matter how intense they were, just wouldn't kick out electrons from the surface of a metal. And Einstein explained this by saying that light exists as what we call photons, discrete packets of energy, units that have specific energy. One photon has one amount of energy. If that amount of energy is enough, an electron will be released from the surface. If it's not enough, an electron won't be released from the surface, no matter how many photons there are. This explanation of the photoelectric effect is the reason that Einstein won a Nobel Prize. It was an incredible piece of thought. And now we completely take it for granted that red light is lower energy than blue light. But at the time, this explanation of the photoelectric effect was completely revolutionary. This black body radiation and the photoelectric effect wasn't the only things that kind of spelt the death of classical physics. We also had this problem of line spectra. Again, it had been well observed for hundreds of years that we see either discrete dark lines in the solar spectra, or we see bright lines for some things when we heat them up. So, for example, if you throw sodium into a flame and look at it through a spectroscope, the yellow colour that you see from sodium is actually two discrete bright lines. This, as I say, had been known for hundreds of years, but again, an explanation to why it goes on had never really managed to be determined. It had been noted that the emission lines and some absorption lines overlapped perfectly. And here I show it with a hydrogen absorption and emission spectra. They perfectly align. And it was also noted that it wasn't the same spectra or even similar spectra for different atoms. By this point, Mendeleev had come along and we had a fairly decent idea of a periodic table. But even periodic trends weren't spotted. It wasn't even a case that the heavier the atom, the more complicated the spectrum became, because iron spectrum is considerably more complicated than that of platinum. These lines, and I show them here on the emission spectra from the sun, are called Fraunhofer lines on the solar spectrum. And again, for a long time, there had been no explanation of them. There had been no explanation of where these lines come from in atoms either. Eventually, it was Bohr who came up with a model of an atom which explained it, but we had various steps to working that out before Bohr came along. The first one was the discovery of helium. So it had been Kirchhoff, who is another kind of great physicist who's had an effect on a large range of modern physics. He had realised that the sodium emission spectrum perfectly overlaid some of these Fraunhofer lines. He also worked out that other elements, hydrogen, oxygen, carbon, were also identified in the sun. Kirchhoff went further to work out that everything up to iron was observed in the solar spectrum of our sun, but nothing heavier than iron was. A little while later, Sir William Ramsay managed to isolate helium from a radioactive mineral. And he didn't know what he'd got, but there were some lines on the sun that had been identified and not been matched with an element. And these lines from this newly isolated thing of Sir William Ramsay matched those lines perfectly. Therefore, this strange emission from radioactive minerals was actually identified as an element in itself, helium, named for Helios, the god of the sun. Nowadays, all of the world's helium is generated from radioactive rocks. Mining helium comes much like mining rocks. Without radioactivity, there would be no helium on Earth today, and therefore no floaty balloons. So just going back to a little bit about what these line spectra are, it had been Balmer who had managed to put a mathematical equation for these lines onto hydrogen. And he basically said that the frequency of this light was related to a constant, and then we had 1 over an integer squared. He didn't know what these integer values were for, but he realised that this perfectly matched what was going on in the line spectrum of hydrogen, but he couldn't get it to work for any other element. So it was Niels Bohr that extended this kind of series of Balmer to actually explain about orbitals in atoms and about how an electron moves between orbitals. So now we're linking our kind of understanding of light with our understanding of chemistry. Niels Bohr said that certain orbitals have certain energy, and as an electron moves between them, it will either absorb light or it will emit light. And now for the first time we have an understanding of what light is in terms of a molecule. Now, for atoms it's very easy. There are only certain numbers of transitions we can see, and we see certain splitting patterns and things like this that make things very complicated. But in hydrogen, one electron makes everything very simple. An important consequence of this is that quantization of energy works for atoms as well as for light. So Planck had said that light is quantized, but now we have that energy levels within atoms and molecules are. Our biggest steps are formed by electronic levels, and then we have vibrational energy levels, rotational, and finally translational, but every one of these energy levels is quantized. One consequence of these kind of new quantum ideas of light is a particle, and our classical theories of light is a wave, has meant that we now understood light having something we call wave-particle duality, the act of light behaving in both of these manners, and essentially we can pick which one suits it best. The biggest change to light theory since the quantum mechanical revolution in the early 20th century, though, has come from Richard Feynman, and Richard Feynman is perhaps the most important scientist of the 20th century. He came up with this theory of quantum electrodynamics, which basically explains how light and matter interact. It brings together the ideas of quantum mechanics and Einstein's theory of special relativity, and essentially does for the quantum mechanics what Maxwell's equations, which had been so fundamental for classical mechanics, had done for classical electromagnetism. One consequence of quantum electrodynamics, though, is that light is neither a wave or a particle. It doesn't have a wave function, which I'm sure you've learned about in your introductory inorganic courses, nor does it have a position probability, which you will learn about next year with Steve Parker. Therefore, light can neither be a particle or a wave. Light is ultimately considerably more complicated than many of the particles around it, such as electrons, which behave by models that we can predict well and easily. So far, the predictions of quantum electrodynamics have not been wrong about a single thing, but understanding them is another matter. I'll finish this lecture here, and I suppose I'm hoping that you leave with an understanding that light is considerably more complex than you even perhaps dared to understand, even those of you that had already heard of wave-particle duality. The fact that Feynman has managed to do away with this wave-particle duality concept does not mean, though, that it is not a valuable way of thinking about light. And I will often talk about light specifically in particle theory to explain transitions within molecules. However, wave theory is incredibly useful when talking about polarization. There becomes a point when our everyday understanding of things can often be more complicated than what actually goes on. However, I think that it's really nice to understand that the world is considerably more complicated and beautiful than we first realise.